On Christmas Eve in 1801, a strange machine stood on the road near Camborne in Cornwall with no horse in front of it. Its weight was obvious before it moved: iron, water, fuel, a boiler, an engine, a frame, wheels, controls, and people all had to travel together. The road beneath it had been made for carts and animals, not for a self-propelled vehicle carrying a live fire and pressurized steam. Yet Richard Trevithick had brought the machine there to answer a question that could no longer be settled in a workshop. Could a steam engine be made compact enough, powerful enough, and controllable enough to carry itself along an ordinary road? Andrew Vivian, a Cornish engineer and businessman who had become closely involved in Trevithick's work, was part of the demonstration and would later be remembered as the man at the controls. When the carriage began to move, the event did not create the modern automobile, nor was it the first attempt to propel a road vehicle by steam. Nicolas Joseph Cugnot had built heavy steam vehicles in France decades earlier. What made Trevithick's experiment distinctive was the kind of engine he was trying to make mobile, a compact high-pressure machine shaped by the industrial problems of Cornwall rather than by any established tradition of automobile design. To understand why he pursued it, the story has to leave the road for a moment and go underground. Cornwall's copper and tin mines were among the places where steam power mattered most in late 18th century Britain. As workings deepened, water became a relentless obstacle. Pumps had to lift it, machinery had to move material, and every improvement that reduced fuel use or increased useful power could have direct economic value. Trevithick, born in 1771 in the Cornish mining district, grew up in an environment where engines were not curiosities displayed for admiration. They were tools judged by whether they could do difficult work reliably. His father was connected with mining, and the younger Trevithick entered a world of engine houses, pumps, boilers, metalwork, and practical calculation. The steam engines already operating in mines had transformed what industry could accomplish, but many were built around one assumption that became a severe disadvantage the moment anyone tried to move them. They were expected to stay where they were installed. A stationary engine could be large because its foundations carried the burden. Massive beams, pumps, masonry, and associated machinery could occupy whatever space the site allowed. Mobility reversed that logic. The moment the power source had to travel, every kilogram became part of the load. A larger boiler might offer useful steam capacity, but would also demand more power to move. Additional water could extend operation while increasing mass. Stronger metal could improve durability, yet punish the vehicle on a hill. A carriage could not simply inherit the architecture of an engine house and expect the road to cooperate. Trevithick's work with high-pressure steam offered a possible way around that problem. Instead of relying on the comparatively low pressures and large arrangements common in older steam practice, he pursued engines in which steam could act with much greater force inside a smaller working package. The attraction was not abstract. A compact engine could be placed where a larger one could never go. It could potentially become portable, and once portability became possible, locomotion ceased to be an absurd idea. The price was risk and engineering difficulty. Higher pressure demanded more from boilers, joints, materials, workmanship, and operators. A vessel that contained pressurized steam could not be treated casually. Weak construction, poor maintenance, low water, or improper operation could produce consequences far more serious than a simple loss of power. Trevithick therefore faced two demands at once. He needed enough pressure to make mobility practical, but he also needed machinery capable of surviving that pressure while being shaken across uneven ground. No automotive industry existed to provide answers. There were no standardized chassis layouts, no established transmissions for heavy road engines, no service network, and no accumulated body of experience explaining how to distribute the weight of a boiler and mechanism on a self-propelled carriage. Each decision had to be made within the limits of contemporary metalworking and steam engineering. The road itself added a second layer of uncertainty. A fixed engine performed against machinery whose geometry could be known in advance. A road vehicle met changing resistance. Ruts, slopes, loose surfaces, curves, and vibration altered the load from one moment to the next. Steering had to work while the machine was producing power. Wheels had to support the full mass and still transfer enough force to the ground to create forward movement. If the carriage reached a gradient, the engine suddenly had to lift the weight of its own equipment as well as whatever people or cargo it carried. What looked like one invention was therefore a collection of tightly connected compromises. Trevithick could not optimize the boiler without affecting weight. He could not simply reinforce the frame without placing a greater burden on the engine. Every additional supply increased the load, making the vehicle harder to move. Yet reducing the structure too far brought its own dangers, as pressure, heat, and the relentless punishment of the road demanded a certain strength. There was no room for excess in either direction. The real challenge was finding the precise balance between strength, weight, power, and durability. Even ordinary fabrication choices acquired new importance. A joint that leaked slightly in a fixed installation might waste fuel. On a moving engine, the same loss could reduce the small reserve of power available for climbing, while vibration made the defect harder to control. Precision, therefore, had to serve mobility as well as efficiency. That was a very different engineering problem from building the strongest possible stationary engine. By around 1800, Trevithick had developed a double-acting high-pressure engine that embodied the direction of his thinking. Pressurized steam could act directly on the piston and produce useful movement from a compact cylinder arrangement. The concept suggested that mechanical power no longer had to remain bound to a large fixed installation. But the road locomotive demanded more than an engine that worked on a bench. It needed a furnace and boiler capable of sustaining operation, a mechanism that could convert piston movement into wheel rotation, a structure that could carry the equipment, and controls that could be managed while the whole assembly was moving. Even if each component worked separately, the carriage would fail if they did not function together under load. This was the real significance of the machine standing near Camborne. Trevithick had reached the point where theory, workshop practice, and mining experience were no longer enough. The vehicle had to reveal its weaknesses in motion. Once steam was raised and the mechanism engaged, the road would test every compromise simultaneously. Before that trial can be understood, however, one part of the machine deserves closer attention. Trevithick's entire attempt depended on taking heat, water, and pressure and turning them into controlled mechanical force inside a package small enough to travel. The answer lay in the relationship between the boiler, the cylinder, and the moving piston. If that relationship failed, nothing else on the carriage mattered. If it succeeded, the remaining problem became one of transmission, traction, control, and endurance. Trevithick's experiment was therefore poised at a boundary between two kinds of engineering: the familiar world in which steam power served a fixed industrial site, and the uncertain world in which the power plant itself had to survive the journey. That boundary became visible inside the working parts of Trevithick's high-pressure engine. The principle was simple enough to describe, but difficult to make reliable in a moving vehicle. Fuel burned beneath or within the boiler arrangement, transferring heat into the water. As the water turned to steam, pressure accumulated. Valves then controlled the admission of steam into the cylinder, where it acted on the piston. In a double-acting engine, steam could be directed to opposite sides of the piston so that useful work was produced on successive strokes, rather than depending on gravity or atmospheric pressure for the return. The piston itself moved in a straight line. A wheel could not use that motion directly, so the engine mechanism had to convert the reciprocating stroke into rotation, and pass that rotation onward to the driving wheels. The full energy path could therefore be followed through the machine. Combustion created heat, heat produced pressurized steam, steam produced piston force, the mechanism converted that force into turning movement, and the wheels finally applied it to the road. Nothing in that chain was optional. A weak fire reduced steam production. Poor boiler performance starved the engine. Inefficient valve control wasted pressure. Friction consumed part of the piston's work. Bad alignment in the linkage could turn useful force into vibration and wear. At the wheels, even a healthy engine could accomplish little if the available traction was inadequate. The challenge was not discovering one miraculous component. It was preserving enough useful energy at every stage that something meaningful remained when the force reached the ground. The boiler sat at the center of this problem because it determined how long the engine could continue working. Trevithick's high-pressure practice also avoided the large condensing arrangements associated with many earlier engines. Exhaust steam could be discharged rather than condensed to create the working cycle, helping simplify the machinery for mobile use, although efficiency and noise were different concerns. Removing bulky auxiliary equipment mattered when every component had to travel with the vehicle. A carriage might move briefly on accumulated pressure and still prove useless if the boiler could not replace the steam being consumed. Sustained locomotion required a balance between the rate at which the fire supplied heat and the rate at which the engine demanded steam. A rising gradient could upset that balance by increasing the load on the piston and forcing the engine to work harder. Greater demand could pull pressure down unless the boiler responded quickly enough. This was one reason mobility placed such severe demands on steam machinery. The engine did not operate against one stable load. The road continuously changed the conditions under which the boiler and cylinder had to cooperate. Water level mattered just as much. A steam boiler required sufficient water to cover the heated surfaces intended to transfer energy safely. Too little water could expose metal to dangerous temperatures. Too much attention to capacity, however, created another problem for a road machine. Water was heavy. Trevithick could not simply carry an enormous reserve without paying for it in additional mass. Fuel created the same contradiction. More fuel extended the period during which the furnace could operate, but every added quantity had to be moved before it could be burned. In a stationary installation, those supplies could be delivered to the engine. On a locomotive carriage, the engine hauled them. The cylinder and piston presented a different set of demands. High-pressure steam made compact power possible because greater pressure acting on the piston could produce substantial force without requiring the same scale of machinery associated with many older low-pressure systems. Yet higher pressure also increased the stress on seals, joints, the cylinder, boiler construction, and valve gear. Leakage wasted the very pressure the design depended upon. Excessive friction reduced output. Poor timing could prevent steam from being used efficiently. Metal surfaces had to withstand repeated motion, while lubrication and maintenance were far less convenient than in a fixed engine house. Then came the mechanical conversion from reciprocation to rotation. The piston drove through rods and cranks or equivalent linkage so that the back and forth stroke could keep a wheel turning. This conversion seems ordinary only because later machinery made it familiar. In an early mobile steam engine, the geometry had to remain effective while the frame was being shaken by the road. The mechanism could not be so massive that it defeated the purpose of compact power, yet it had to be strong enough to endure repeated loads. The force reaching the driving wheels then met a final physical test: adhesion. The wheels needed sufficient grip to push backward against the road, and therefore move the carriage forward. If the surface was loose or slippery, rotation could be wasted in wheel slip. If the surface was rough, resistance increased. A hill raised the required tractive effort. Every change outside the engine altered the demands inside it. Steering complicated matters further because a powered vehicle could not simply follow the line of a wagon pulled by an animal that supplied both traction and directional control. Mechanical propulsion separated those functions. The engine provided force, while the vehicle's steering arrangement had to guide a heavy structure carrying machinery whose weight distribution was unlike that of an ordinary coach. The operator, therefore, had a job far more complicated than that of a later motorist. Managing speed or direction was only part of it. Someone also had to understand the fire, the water, the pressure, the valves, and the behavior of exposed mechanical parts. A road locomotive was less a carriage with an engine added than a mobile engine installation that happened to carry people. This is where Andrew Vivian's participation becomes more than a biographical detail. Vivian had practical experience in the Cornish mining world and was involved closely enough with Trevithick's work to operate the Camborne machine during its public demonstration. The experiment depended on judgment at the controls because the machinery did not regulate itself in the way later vehicles would. The operators had to interpret what the engine was doing while also responding to the road. A decline in performance might indicate a changing gradient, falling steam pressure, poor combustion, friction, or another mechanical issue. A successful journey required the crew to manage the machine as a dynamic system rather than a collection of separate devices. Trevithick's approach gave that system a chance because high-pressure steam concentrated useful force into a smaller engine. It did not remove the compromises surrounding mobility. Instead, it made them worth confronting. Once the basic operating cycle was established, every later improvement could be judged by what it did to the balance between power, weight, durability, and control. That is why the December 1801 trial mattered as an engineering test. The carriage was no longer being asked merely to demonstrate that its piston moved or its wheels could turn while suspended. It had to prove that the boiler could keep up, the mechanism could remain aligned, the tires and wheels could carry the load, the steering could be managed, and the engine could overcome the resistance imposed by a real road. The machine's internal logic had been assembled. What remained uncertain was whether that logic could survive contact with terrain. On Christmas Eve, Trevithick and Vivian were about to discover how much difference a hill could make. The hill turned the demonstration from spectacle into measurement. On level ground, the carriage mainly had to overcome rolling resistance, friction, and the inertia of its own mass. On an incline, gravity added a continuous opposing force, and every part of the vehicle suddenly became more expensive in mechanical terms. The boiler, frame, engine, supplies, crew, and passengers were not simply being carried. They were being lifted. Trevithick had designed the machine around the hope that compact high-pressure power could offset that burden. The road now had the final say. With Andrew Vivian at the controls during the Christmas Eve demonstration, the locomotive moved through Camborne under its own power and climbed, showing that the engine could produce enough tractive effort to propel a complete road machine rather than merely spin its mechanism in place. Speed was almost beside the point. The important result was that the vehicle continued to move while carrying the apparatus necessary for its own operation. That success, however, should not be mistaken for proof that practical road transport had been solved. A short public demonstration compressed the hardest questions into minutes. A transportation system had to answer them day after day. The carriage would need to cope with changing gradients, poorer surfaces, repeated stops, fresh loads, wear, maintenance, water consumption, fuel supply, and operators who could reproduce the performance without Trevithick's immediate presence. The difference between those two standards was enormous. A prototype only had to show that a principle could work. A useful vehicle had to make that principle dependable. The Camborne trial exposed why reliability would be difficult. One successful climb could establish capability, but it could not reveal the full rate of wear, the frequency of adjustment, or the cost of keeping the machine ready for another journey. Those answers only emerged through repeated operation. Road shock affected more than passenger comfort. A heavy boiler and engine placed large loads on the frame and wheels, and irregular surfaces repeatedly disturbed the alignment of moving parts. Every joint and bearing had to tolerate vibration while the vehicle remained hot and under pressure. Steering demanded attention at the same time that the engine required management. The crew could not simply set the machine in motion and become passengers. They had to listen to it, watch it, and respond to changing conditions. Early steam locomotion was therefore inseparable from skilled operation. The machine's behavior could change as the road rose, as the fire weakened, or as mechanical resistance increased. Even without a dramatic failure, performance could decline gradually until the vehicle no longer had enough reserve to continue effectively. The road also imposed a limit that had nothing to do with the engine's theoretical output. Traction depended on the condition of the surface beneath the driving wheels. A powerful engine could not use force that the ground would not accept. On a firm surface, the wheels could push effectively and convert rotation into forward motion. On loose or uneven ground, some of that effort could be lost. The vehicle was therefore tied to the quality of infrastructure in a way that horse-drawn transport was not. Horses were imperfect machines, but they could choose their footing, adjust their stride, and respond instinctively to terrain. Trevithick's Carriage replaced that adaptability with mechanical precision, and the roads of 1801 offered little precision in return. The passengers, if they expected anything resembling a coach journey, would have encountered another contrast. There was no meaningful separation between the transportation system and the industrial machinery producing motion. Heat, noise, smoke, vibration, and exposed moving parts belonged to the experience. The vehicle had been conceived by men accustomed to steam engines in mines and workshops, not by an industry devoted to comfort, suspension, weather protection, or ergonomic control. From a modern perspective, it is tempting to treat these qualities as evidence that the machine was crude. A more useful interpretation is that Trevithick was solving a different problem first. Before comfort could matter, propulsion had to become possible. Before refinement could matter, the vehicle had to prove that the engine could survive outside a fixed installation. Camborne supplied that proof in a limited but important form. It also exposed the distance between mechanical possibility and economic usefulness. Trevithick was not competing against a fleet of other motor vehicles. His real comparison was with horses, carts, and coaches, supported by a mature network of skills and services. Horse transport had obvious costs. Animals required feed, rest, shelter, care, replacement, and human labor. Yet those costs were understood. Stables existed, farriers existed. Coach builders knew their craft. Inns and posting systems served established routes. A steam carriage introduced a different set of requirements without removing the old problems of roads, weather, and maintenance. It needed specialized metalwork, boiler knowledge, fuel, water, and operators capable of managing machinery under pressure. A vehicle could be technically impressive and still fail to offer a compelling economic advantage. That distinction would become increasingly important after the first excitement of demonstration faded. Trevithick had shown that the machine could move, but the next questions were harsher. How often could it move? How far? With how much useful load? At what cost? And with what reliability? Those were not questions a single Christmas Eve run could settle, nor could they be answered by simply increasing pressure or making the engine larger. More power might help on a hill while increasing stress elsewhere. Greater strength might improve durability while adding mass. Carrying more water might extend range while making acceleration and climbing harder. The entire vehicle remained a negotiation among competing demands. That is why the road experiment should not be treated as a failed automobile waiting to become modern. It was an early attempt to discover what self-propelled road transport required before anyone possessed a mature design language for such machines. Trevithick learned by forcing the prototype into the environment where its weaknesses became visible. The result was neither a commercial breakthrough nor a dead end. It was evidence. High-pressure steam could move a full-sized vehicle on a public road. The surrounding system was far less ready. Trevithick responded not by abandoning mobile power, but by continuing to develop the engine and by seeking situations in which its strengths might matter more than its disadvantages. The next stage would involve patent protection, another road carriage, and a more ambitious test in London, where novelty would have to confront the economics and expectations of an established transport market. The lesson was beginning to separate two questions that had seemed identical at Camborne. One concerned propulsion. Could an engine create enough useful force to move a complete vehicle? The other concerned service. Could that vehicle become something people would choose repeatedly over familiar alternatives? The first question had received a convincing answer. The second remained almost untouched. That distinction mattered because invention often becomes less dramatic precisely when it approaches everyday use. A demonstration can be arranged around favorable circumstances and close supervision. Routine transport cannot. It must tolerate delays, imperfect maintenance, changing loads, and ordinary operators. It must also justify the cost of building and supporting an entirely new mechanical system. Trevithick's next road experiment would therefore face a much less forgiving standard than the Camborne run. In London, the machine would be seen not only as a technical curiosity, but as a potential means of carrying people through a city that already possessed coaches, traffic, commercial expectations, and established habits. The pressure on the engine would be joined by pressure from the market. That market pressure exposed the difference between an engine that could move and a transport system that could survive. In March 1802, Trevithick and Andrew Vivian secured a patent associated with their high-pressure non-condensing engine work, giving formal shape to ideas that could be used in both stationary and locomotive applications. The patent did not solve the practical difficulties of road transport, but it marked an important change in the scale of their ambition. The machinery was no longer tied to one experimental carriage. It represented a broader engine system that might be adapted to different tasks if the surrounding engineering could support it. Trevithick soon returned to the road. In 1803, another steam carriage linked to his work was demonstrated in London. The setting was very different from Camborne. Cornwall had supplied an industrial culture familiar with steam machinery and a relatively direct connection between engineering experiments and mining problems. London offered crowded streets, established coach traffic, potential passengers, and a commercial environment in which a self-propelled carriage would be judged against services that already worked. The challenge was no longer simply to prove movement. The machine had to justify its presence. That proved far harder. A passenger vehicle had to offer more than mechanical novelty. It needed workable operating costs, acceptable reliability, manageable maintenance, reasonable comfort, and some advantage significant enough to outweigh the inconvenience of supporting unfamiliar technology. The London carriage did not create a sustainable road transport business. That failure is sometimes treated as evidence that steam road locomotion was simply premature. But the more revealing explanation lies in the number of systems that had to mature together. The engine could be compact and still be expensive to maintain. The vehicle could carry passengers and still be awkward to operate. The machinery could produce adequate power and still suffer on unsuitable roads. No single improvement would automatically turn the experiment into a service. Public roads themselves were becoming a major part of the problem. A heavy-powered vehicle encountered resistance that varied from one surface to another, and its concentrated mass punished components designed around coach construction rather than industrial machinery. Steering a substantial engine carriage through ordinary traffic added further complexity. Horse-drawn vehicles benefited from an animal that supplied traction, adapted its footing, and responded continuously to the road. Mechanical propulsion separated those functions and forced engineers to solve them with hardware. The more Trevithick demonstrated that the engine could work, the more obvious it became that the environment beneath and around the machine could determine whether the power was useful. Britain already possessed another transportation environment where heavy loads moved along prepared routes. Mines, quarries, ironworks, and industrial districts used wagonways and tramroads to guide wheeled vehicles along fixed tracks. Many still relied on horses or gravity, but the track changed the mechanical equation. Direction no longer depended on free steering. Rolling resistance could be reduced, and a vehicle could be designed around a known route rather than every irregularity of a public road. For high-pressure steam, this offered an opportunity. Instead of asking one machine to tolerate almost unlimited road conditions, engineers could pair the engine with infrastructure designed to constrain and support its movement. Rails did not remove difficulty. They merely changed its form. One concern was adhesion. Some engineers questioned whether smooth metal driving wheels could develop enough grip on smooth rails to haul useful loads without slipping. Another was structural. Early tramroads had been built for wagons, not for locomotives, carrying boilers, cylinders, frames, and fuel. A heavy engine might produce adequate tractive effort while damaging the track under its own weight. Yet those problems were attractive precisely because they were measurable. An industrial railway presented a specific route, a known load, and a clear economic purpose. A locomotive did not need to compete with a passenger coach on comfort if its job was to haul iron or coal more effectively. A fixed industrial route also made support easier to organize. Fuel, water, maintenance, and loading points could be planned around known locations rather than carried into an open-ended road network. It could be judged by tonnage, distance, operating expense, reliability, and the condition of the track after repeated use. That was much closer to the practical engineering culture from which Trevithick had emerged. South Wales provided the next important setting. At the Penydarren ironworks near Merthyr Tydfil, Samuel Homfray became interested in Trevithick's high-pressure engine and in the possibility of using steam power on the tramroad connected with the works. The task was direct: move a substantial industrial load along rails. For Trevithick, the change in environment allowed the same basic engine philosophy to be tested against a new kind of resistance. The locomotive no longer needed to steer through ordinary roads or offer a tolerable passenger service. Its route was fixed, and its usefulness could be measured in work performed. But the shift also exposed a new engineering relationship. A locomotive and a railway could not be considered separately. The machine might be powerful enough to haul a train, yet the rails had to support the concentrated loads imposed by the locomotive. Stronger track increased infrastructure cost. A lighter engine reduced stress but risked sacrificing adhesion or useful power. Once again, progress depended on balance. During the winter of 1803 and 1804, a locomotive was built at Penydarren around Trevithick's high-pressure principles. The machine represented a different answer to the mobility problem than the road carriage had offered. Cameron had asked whether self-propulsion could survive an ordinary road. London had tested whether such a vehicle could become commercially persuasive in an existing transport market. Penydarren would ask whether the engine could earn its place by doing heavy industrial work on a controlled road. That was a stricter test in one sense, and a fairer one in another. There would be no need to argue about novelty if the locomotive could move a load that otherwise required animal traction. There would also be nowhere for weak infrastructure to hide. On 21st February 1804, the machine was prepared for a journey that would place not merely its own weight, but a substantial train behind it. The unresolved question was no longer whether steam could produce motion. It was whether the engine, the wheels, the rails, and the load could function together long enough to make that motion useful. The stakes were practical enough to strip away much of the romance that later attached to early locomotives. If the engine slipped, broke down, or consumed too much fuel for the work accomplished, the experiment would have little value. If the track failed, the weakness of the overall system would be just as decisive as a weakness in the locomotive. Industrial transport required repeatability, not a single dramatic movement. Penydarren therefore offered Trevithick something London had not: a setting where success and failure could be judged against a specific commercial task. The locomotive would have to pull real material over real distance on infrastructure that had not been created for it. That combination made the trial more consequential than another demonstration before spectators. It would reveal whether mobile high-pressure steam could move beyond self-propulsion and become a tool for hauling weight, while also showing which parts of the surrounding railway were not yet ready for the forces such an engine introduced. On 21st February 1804, the Penydarren locomotive was put to work on the tram road toward Abercynon with 5 wagons carrying roughly 10 tons of iron and around 70 men. The journey covered about 9 3/4 miles. By the standards of later railways, the speed and arrangement were modest. By the standards of the experiment, the result was decisive. Trevithick's locomotive hauled a substantial load along iron rails under steam power. The question of whether smooth driving wheels could generate enough adhesion for useful traction had received a practical answer. The machine did not need toothed rails or some separate gripping mechanism to move the train. Its own weight pressing the wheels against the track could provide enough adhesion for the task. Yet the trial also uncovered a limitation that would shape the immediate fate of the locomotive. The cast iron tram road had not been designed for the concentrated weight and dynamic forces of a heavy steam engine. Rails broke under the loads. The problem was no longer an inability to produce motion. It was a mismatch between the locomotive and the infrastructure carrying it. That reversal captures the central pattern running through Trevithick's experiments. Each time one barrier was crossed, another became visible. Compact high-pressure power made mobility possible, but public roads exposed difficulties of resistance, steering, service, and economics. Rails reduced some of those problems, but the heavier locomotive demanded a stronger railway. Engineering progress did not proceed because one invention arrived complete. It advanced by revealing the next constraint. Penydarren therefore deserves attention not because it was a finished railway system, but because it demonstrated both the promise and the incompleteness of steam traction at the same moment. The locomotive did not establish a lasting service there. Track damage and practical difficulties prevented the experiment from becoming a routine locomotive operation, and the engine was later used in stationary work. Trevithick, nevertheless, continued exploring locomotion. Other locomotives associated with his designs appeared in 1805 and again in 1808, including the well-known London Exhibition locomotive, later called Catch Me Who Can. None created the stable commercial railway enterprise that would emerge in subsequent decades. Trevithick's career moved into other engineering projects and eventually took him abroad, while locomotive development continued in industrial districts, where repeated hauling work gave engineers strong reasons to improve both engines and track. That later history matters because it prevents a simple, heroic narrative. Steam railways were not invented in one moment by one man. Engineers, colliery owners, iron founders, mechanics, investors, and railway operators gradually solved different parts of the system. Track became stronger. Locomotives became more reliable. Boiler and valve arrangements improved. Operating practices developed. Industrial railways created environments in which machines could be tested repeatedly rather than displayed occasionally. Figures such as George Stephenson and Timothy Hackworth worked within this later phase, when the problem was no longer merely whether a locomotive could move, but how to make locomotive transport dependable enough for sustained service. By the opening of the Stockton and Darlington Railway in 1825 and the Liverpool and Manchester Railway in 1830, steam locomotion had entered a different historical stage. A railway could now be conceived as an integrated commercial system in which track, motive power, traffic, maintenance, scheduling, and investment were planned together. Trevithick had not supplied that complete model. What he had supplied was evidence that changed the range of possibilities available to those who followed. His early machines showed that high-pressure steam could be compact enough for locomotion, that a road vehicle could carry a working engine, and that a rail locomotive could haul a meaningful load by adhesion alone. Just as importantly, his failures exposed why those achievements were not sufficient. The London Carriage demonstrated that a technically functioning vehicle could still lack a viable market in supporting infrastructure. Penydarren showed that a capable locomotive could be limited by weak track. These were not embarrassing footnotes to a success story. They were part of the engineering knowledge created by the experiments. Seen this way, the Christmas Eve carriage of 1801 takes on a more precise historical meaning. It was neither the first self-propelled vehicle in human history, nor a disguised version of the modern automobile. It belonged to the steam age and to the specific problems of mining, metalworking, and early industrial transport. Its importance came from the decision to make a high-pressure engine travel, and then confront the consequences of that decision in the real world. Trevithick did not have the benefit of standardized components, proven road vehicle layouts, strong railway infrastructure, or a mature industry ready to manufacture and maintain locomotives. His prototypes had to discover the limits of their environment while testing the limits of the machinery. That is why the story should not end with the claim that one successful run changed transportation forever. The transformation took decades and depended on many people. A more defensible conclusion is that Trevithick helped move steam engineering into a new category of problem. Before locomotion, the central question was how effectively an engine could perform useful work at a fixed site. Once the engine itself moved, engineers also had to think about weight distribution, traction, route conditions, infrastructure strength, operating range, maintenance away from an engine house, and the economics of replacing established forms of transport. Those questions became fundamental to every later attempt to build practical mechanical transportation, even when the technologies used to answer them changed. Trevithick's machines did not settle the future. They made parts of that future technically imaginable and, more importantly, measurable. A road could expose whether a vehicle had enough tractive effort. A railway could reveal whether a load could be hauled efficiently. Broken rails could show that infrastructure needed to change. A failed commercial service could show that engineering performance and economic usefulness were not the same thing. By turning ideas into machines, Trevithick forced each claim to meet physical evidence. That may be the most enduring feature of his work. The Great Leap was not a prophecy of the automobile or the modern railway. It was the insistence that concentrated steam power could leave the fixed installation and be tested as a moving system. Once that happened, locomotion stopped being only a speculative possibility and became an engineering problem with observable results, costs, failures, and improvements. The machine that climbed a Cornish road in 1801 did not arrive with a transportation revolution behind it. It arrived before the roads, rails, businesses, and operating knowledge required to make such machines ordinary. 3 years later, Penydarren showed the same contradiction on a larger scale. The locomotive could pull the load, but the railway beneath it was not yet strong enough. That tension between what an engine could do and what the surrounding system could support would define the next generation of development. Trevithick's contribution was to push hard enough against the limits of his own age that those limits became visible. In that sense, the value of the experiments lay as much in the boundaries they exposed as in the motion they achieved. Later railway engineering would advance by strengthening the entire system around the locomotive, not by treating the engine as an isolated invention.